afternoon. This is CIVE632, Computational Hydraulics and Hydrology. Today is Monday, October 18. And the topic today is the last lecture on diffusion wave modeling and the first one or two lectures on dynamic wave modeling. So let me just get started in there, and I'll put it in the right place and then share the screen with you. No, yeah, right, share the screen. That's what I need to do. Okay. Yeah. What can you see in there? Or what are you seeing? Well, let me back up. No, I can't do that. Yeah. Let me just say that the last section or the last article on that last week was the thesis by Rosa Aguilar. And what I'm showing in here is the model that she put together. And what I'm going to do today, at the beginning, maybe 20 minutes or 30 minutes, is explain what she did using all the concepts that I've been talking about for 8 weeks, and then also run the calculator, and you have in there the calculator, so that you can see how these things are done. In 1986, we wrote that paper, which was a very well received paper, and we just had at the time the right tools to put it all together, and it worked really well. And what took me so long to get into the online stream, I do not know. I guess we were waiting for the right student. So Rosa came around in the year 2012, and she signed up in the lab, and then she said she wanted to do a thesis. So that's when I found my chance, my opportunity. So I asked Rosa to do the translation of the Fortran program into PHP. And I consider that to be a thesis itself, because people are not familiar with the new programming languages and so forth. And besides, the content of the stuff was extremely complex and very numerical, and she had studied all the courses that I offered, so she was ready. So after a year of preparing, she undertook on the second year that she was in the lab to do this work, which I am now going to present to you so that you can see it. And I am kind of coalescing, putting all things together that we already discussed. So many of the things that I'm going to say today will be repetitive, which is good. That's the way it should be. So we have in here the paper, the original paper, Diffusion Wave Modeling of Catchment Dynamics. We already have seen it. Engineering Hydrology Principles and Practices. In my book, published in 1989, I wrote a complete section on this stuff, on the small catchment hydrology part, chapter 4. So now I'm going to show you or get into the thesis by Rosa. We call it Diffusion Wave Modeling of Catchment Dynamics, the same paper title, but using online calculation. Let me remind you that there's a couple of people in Italy that 10 years later wrote a paper on the same subject. I think his name was Professor, and honestly, I don't remember the name, but they wrote a paper on the same subject. All they did was they added another word in there, distributed catchment dynamics. Yes, you could make a point that that this catchment dynamics that we deal with is distributed, so it's kind of reiterative to say that. So this is Rosa's thesis on the web. We put it on the web. The thesis exists as a thesis, and it's in the library and so forth. We, to be honest with you, have not been around or not gotten around to publish this paper or this work. I can't explain why. A lot of people like to publish, We feel that we have already published it. The minute we put it on the web, it's already published. Okay, Rosa wasn't in a hurry to do any publishing. She went on to work with West, and she now works with West. She's been with West since spring of 2014, so she has spent 7 years working with West. So she's out there happy and so forth. And the people of West are happy with her. I know, pretty sure. And so she's out there. And today I'm going to be discussing what she did. Basically, she had to go through the methodology, which is all theory, of course, equations and so forth, and then come up with the algorithms in PHP. And in order to do that, I had to teach her PHP, and she was willing to do that. I should tell you that not many people are willing to go into programming, but I know that programming is the secret to success. Programming, not the other stuff that most people use. So that was good. That was a good experience for her. An analogy is like this, and I'm going to share with you this analogy. When people go into Camp Pendleton, the Marines, you want to become a Marine, you go to Camp Pendleton. And they get you in, right? And you go through training. I don't know exactly what they call it, training to become a Marine. And they make you do all sorts of things, like push-ups, 100 push-ups, and you got to do them. There's no way out of that one. He or she could not do 100 push-ups is out of the program, right? Now, when you're actually going out there to do the fighting, you're not going to do push-ups in front of 100 push-ups in front of the enemy, right? But they require to do 100 push-ups only because that is the way to assure that that person is fit, physically fit, so that he can do other things later on. The same thing with us. What Rosa did was 100 push-ups with this work, as you can see later on. And now she's prepared to do 20 or 15. You see, that's the way it's usually done in the real world. When you go to school, it's more strenuous. And then eventually it's kind of relaxed, but because you had or you ran through the experience, it is better. So I'm going to touch base on the equations. And the equations, you should be familiar with all the equations. And if you're not, you go back and review the stuff on your own time. Okay? Mathematical models have been developed in the 60s. Wright, Woolheiser, Wooding, Shaki. Those are the big names. Essential problem is to determine the flow off the plane for geometric, hydraulic, and hydrologic conditions, DUG. The concept of kinematic wave is well established. The diffusion wave for the analysis of overland flow is now well established. That's the one we're talking about here. The kinematic wave was done on the plane, as I told you, by these three gentlemen, Woolheiser, Wooding, and Shaki, but they use kinematic wave, not diffusion wave. So if there was an issue of discretization, then their problems or their solutions were going to be grid dependent. No question about it. Okay, so if the wave was diffusive, it wasn't going to show the true diffusion. And if the wave was kinematic, it's going to diffuse anyway. So they were in a duality in there. Granted, though, not too many people at the time realized that was going on. It was only after Conch came out, and Conch came several years later. Those three gentlemen that I've been talking to you about. Okay, so the term diffusion is used in this thesis to refer to the diffusion of momentum, as opposed to that of mass or energy. She is now trying to distinguish between the term diffusion and dispersion, and there has been some confusion in the literature. Diffusion may be extended to the realm of dynamic waves by incorporating the fluid number dependence of the hydraulic diffusivity. You know, this is Doug's subject and also my subject. So we introduce the Vedernikov number here to convert the kinematic diffusivity or just the plane diffusivity to dynamic diffusivity. We call it dynamic diffusivity because by introducing the Veternikov number, the system becomes dynamic. Okay, the diffusion wave method is not only grid independent, but also capable of minimizing numerical dispersion. Because if there is dispersion, since we're not considering dispersion in the calculation, we should eliminate it. And to do that, we know how to do it. We take the Courant number set equal 1, and at that point, the whole thing nicely gets into the category of a diffusion wave without grid dependence. What I say in grid independence, based on the Muskingum-Gunch method, is attained by matching the numerical diffusion of the discrete model with the physical diffusion of the analytical model. Okay, and I give an example of Ponce and Chaganti. If you would recall, Chaganti helped me show that in fact Muskingum-Gunch method was a good method, reproducible, accurate, etc. Not the hocus pocus that people have been talking about. People didn't understand the numerical diffusion. We're referring to it as hocus pocus. I don't even want to remember where, but it's out there. If you're curious, go out there and review all the journal papers from hydraulics division or hydraulic engineering from 85 to 90, and you will find it. Okay, so the objective is to develop an online diffusion wave model of catchment dynamics. I should mention to you, if I haven't mentioned this yet, that 10 years later, 10 years after the writing of my paper, I met a person in Monterrey, Mexico. I was in Monterrey, Mexico for a conference. They invited me, and I met this gentleman, and we got into talking. And I said, "What are you doing?" He says he was with the Danish Hydraulics, which is a big outfit. I'm told they have about 100 PhDs employed in their staff, on their staff. And so there's a big outfit, consulting, international consulting. So I asked him, I said, "What are you guys doing?" And he says, "Well, we're getting into the diffusion wave model." That 10 years after we had done it, which is fine. I mean, that's how long it should take, or that's how long it does take. So you can see these things are actually being applied. I take that back. It was not 10 years. 10 years was the Italian experience, but with this gentleman from Canada, it was more like 25 years. It was in the year 2012 or 2013. Okay, scope then. The development of the online diffusion is what the open source general purpose PHP. That's an open source program. Open source, as you maybe know, means it's free. You can download it from the web. You don't have to pay anybody anything. There's two kinds of. I don't want to sidetrack myself, but there's you either get open source programming or software, or you buy it. It's up to you to decide that. Okay, the online calculation is accomplished with PHP, and input and output is designed using HTML. PHP carries on the computation while HTML displays the input and output. PHP and HTML, while I'm talking about this, I should tell you that they have an interesting marriage, because you can't do really HTML computations without an engine, and then the engine is PHP. But if you use the engine, you couldn't show it. So therefore, you need the HTML to show the results. So it's a good marriage. The interesting thing about this is that the PHP does not show. So in other words, people cannot copy your code. Even though the code is free, they can't copy it. Unlike other programs or software methodologies that you can write it up, you put it on the browser, and people can cut and paste your program into their computer. As a matter of fact, we have a computer program which 20 years ago, more than 20, like 22 years ago, we kind of got from the web. Because I asked one of my students, I said, "We need this program." And I was thinking we were going to develop it. I was kind of charging him to develop the program. And he said, "Professor Ponce, we don't need to do that. I found a program. This program does what we want to do, so that's it. Let's run with it." And I at the time said, "Well, okay, fine." And we still have that program running in our computer, even though it's not ours. We don't even know who the program is, but it works, okay? So the model is tested for volume conservation, and we're going to choose in here um, the various parameters of the problem, right? Rainfall intensity, rainfall duration, overland flow area. We're trying to get some numbers in here that will have a nice output because we want to analyze the output and it has to be nice, meaning whole numbers, okay? Fraction of area on the left plane, fraction of peak flow used to estimate reference discharge, because we do this is not a variable parameter, it's a constant parameter. So you need a reference discharge. Curve number, 180. Well, this is not computational. We had to put into the curve number. And that was not easy. I told Rosa it had to be done. And then when she was doing it, she ran into trouble. It wasn't easy. But we got together and we did it. It took us about a week's time to work this stuff in the curve number. Because if you say the curve number is 100, then it's easy. Everything runs off. But if it's 80, then you got to put in there the curve number methodology, and that's not easy. Not so much the curve number, but the actual algorithm to make sure that any distribution of precipitation actually gets accounted for. So rainfall distribution, you can have 2, 3, 4, and 5 points. Yeah, I'll talk about that in a little more detail later. The theoretical background. So now I'm going to throw at you equations, a lot of equations, and I'm going to throw them at you fast because you're supposed to relate to these already. 2, 1, and 2 are the basic equations that we're solving. Basic equations. QS, okay, this is the depth of the surface. This is a rating curve, okay. 2, 4 is Southern law. That's the Southern law, the celerity of a kinematic wave. 2, 5, maybe I have not talked about this, but this is the Woolheiser kinematic flow number. When Woolheiser did his work, he was getting a PhD over at Cornell with Liggett, and they developed this number because they realized that there was an issue of applicability of the kinematic wave. And therefore, he came up with this number. And look at this number, S in the numerator. So the greater the S, the more the kinematic wave is applicable. So this is kind of related to the same thing we did, only that we did it with using linear stability, using the S curve, and we were using it. The difference between our treatment and Woolheiser's treatment is that Woolheiser was using a plane that has limit. It's a finite plane, while we were using an infinite channel and an LSAO. We were using the LSAO. Okay. But there's an LSAO in there too. So is that the same LSAO? No, Woolheiser was not using our LSAO. He was using his LSAO, which was the length of the plane. As in there it says very clearly, LSAO, length of the plane. Okay, then Du comes in. Then we come in 1986, and we define the Courant number. We'll redefine the Courant number. And that's the definition of the Courant number. Fundamental concept in open channel hydraulics. I extensively have talked about this already. The wave models, the kinematic wave modeling based on this equation 2.7, and then plugged in into into the continuity equation gives us equation 2.8. So that's the equation that McCarthy solved unsuspectingly. He didn't think, McCarthy went to the field and measured a whole bunch of things, storage. He was intent of correlating storage with Q. In other words, the Q with the storage. His understanding that at the time, that would be his line of thought. But then eventually he came out with a method, or came around with a method that his guns showed 31 years later, it was in fact it was this equation, 2.8. Then the numerical solution, we already know that. We have our C's in here. We already know that. Then there's 3 methods. Remember the convex, which is on the right-hand corner. The Lie, which is on the right-hand top of the right-hand corner. And then there's our method, which is not in any corner. Our method is actually varying with the C and with the D along the central axis. Okay, so this gets to the routing equations for the various schemes. We don't have to worry about it at this point because we're just going to run the model that is going to have implicit, everything in the model has already been done. Diffusion wave model. Okay, I do want to say that when you do something like this, you have to know the answer of the model. If you don't know the answer, you cannot do the model because there's umpteen ways of this thing going wrong. I mean, so many, it's unbelievable. And if it goes wrong in one of the 1,300, it will not give you the answer. That's just the sensibility or the sensitivity, it's the sensitivity of the numerical method. So we had an answer. How is it that we had an answer? Because we had already run the Fortran program, and it was giving us mass conservation, and it was giving us consistency. Everything was okay. So we were trying to emulate the Fortran program, and we did, by the way. Everything came out. The difference, of course, being that if the Fortran program runs in 1 second, the PHP runs in 10 seconds. Why is the PHP so inefficient? And the answer is Fortran only does one thing, floating point calculations. I mean, any calculation. While PHP has several balls to look around. They do a lot of things. PHP does a lot of, actually PHP you can do just about anything. And I know there's various engines on the web, but PHP is one of them. It was after PHP that we started getting fancy on the web. At the beginning, the web was kind of dumb, meaning they will post a paper and you can read it. That was it. Now, the first 5 years, it was like that. Until PHP came about in the year 2000, 1999. And there were other methodologies and so forth. The technology advanced rather quickly at the end of the century. The first 5 years, it was not as fast. I know because I've seen it. I lived through it. So it started advancing and PHP came up, developed a whole lot of things. Facebook, I believe, was developed with or with the aid of PHP. And that's only one out of so many. Okay, diffusion wave equation, we already know that, 211, 219, that's the equation of Hayami, where the diffusivity is this, we already know that, and that leads to our famous formulas, in which D now, in complementing the C now, D is, we call it a cell Reynolds number. We introduced that concept, and it's there. It's a cell Reynolds number. And I think I already told you that it's a reciprocal of the cell Reynolds number of that's given in the book of fluid mechanics, because I didn't want to change the ratios. It was supposed to be the ratio of physical diffusivity to numerical diffusivity. And Roche, when he wrote his book in 1972, he reversed it. He put the numerical in the numerator and the physical. I thought that was wrong. So I didn't follow Roche. I followed Roche in the name only. Roche was a good book. I read all that book. Then the diffusion wave, the dynamic wave modeling, equation 227, that's the Professor Duke's associates equation, okay? And 228 is what we use in our program. 229 is the definition of the Vedernikov and Fruit number, which I developed in 1991. We recently came up with the biological data, or rather biodata, for Professor Vedernikov. I don't think I told you this. I charged one of our students to do that, and it took him a while. But I told him there's no hurry. You can do it, I mean, within reasonable time. Well, it took him a couple of years or 3 years. Everybody's busy, you know. But he had to get the data from Russia, and he told me that it was not easy. But he finally, persisting, he got it. And he sent me the picture, and I got the picture, put it on my website, on my papers. Then he recently sent me the biodata. I can show it to you later on. It's already on the web. Vedernikov was a civil engineer working at an agency in Russia that is kind of the Bureau of Reclamation. He was in charge of irrigation. He was charged with doing infiltration from channels, because you know channels lose water, and we want to know how much and where, etc., the head and so forth. So he did that for a long time. But somehow, because I don't know the details, because the biography was not more than 100 words, but somehow he got involved in this issue roll waves, and he came up with this concept, which we now call the Vedernikov number. But interestingly, since the subject is complex, and at the time he didn't know everything he needed to know about, he kind of made it very confusing. It's very confusing. The subject could get really extremely confusing. Other people could not model through his stuff, so he was basically ignored for a long time. Kraya came in the year 1952 and said, you know, Paternico, he's a good guy and he's got all his stuff done well, but in reality, there's these Rolls waves happen when the dynamic waves overcome the kinematic waves. It's not supposed to be like that, but when it is, then it happens. That's when I came in, because I already knew my dynamic waves and my kinematic waves, and I was able to sort it out and put it all together in the year 1991, making it easy, kid stuff, to understand these concepts. It's no longer scientist, Vedernico, hydraulic genius guy. Okay, and the cell Reynolds number, of course, Chow did not throw any light. Chow, all he did was just copy what Vedernico had said. And the cell Reynolds numbers is this. Now, model description. Let me go out here and here. Then she talks about the discretization, the hydrologic abstractions, the spatial geometry, routing in the plane. So here is the crucial thing for us. The Muskingum method is used to develop the equation. Equation has 4 routing coefficients. Matching physical and numerical diffusivity enables the grid independence. The only method that is grid independent is the one that matches. Okay? So if you give a delta t, then the model, in order to force a Courant number equal 1, has to set the delta x equal to c delta t. C already know. We delta no. So in other words, c delta t will give you the delta x. In other words, this is an interesting, funny, quote unquote model that you got to give it, that the delta t is already defined by the delta s, that is the space step. We call it s in here because it goes it goes in x and y. So we call it s, space. So it's c delta t. This kind of trick occurred to me kind of early, like certainly more than 30 years ago, because we figured out that's the way we would do it. Otherwise, you set the delta S, you set the delta T, and you're by chance hitting it at Courant 1. To eliminate the issue of chance, we made this equation. We forced the system to be equal to 1. Okay, so what happens is this, that when it runs the model, you have a plane in there, it has a certain length, okay? And it says, I want you to put 3.7 steps in here. The model says that. And of course, 3.7, you cannot put 3.7 steps. It has to be the 3 or 4. Okay, then we have the model choose. If it's 3.7, then it's going to be 4. If it's 3.3, it's going to be 3, right? But the model is so good that it not only works for Courant equal 1, it also works for Courant equal 0.9 or 0.6, I'm sorry, 0.7 or 1.1, 1.2, because we already know that that is the case because we have studied our phase, amplitude, and phase portraits. I've already shown those things to you, and we will continue to, I already shown those things. That's the work that Marcela Diaz did 5 years ago for us, setting up the calculators for the amplitude and phase portraits. Okay, the hydrologic abstractions, I'm not going to spend a whole lot of time because this is another subject. We just put it in there. Those of you that have taken hydrology with me last year know that these equations are the Marcus's equations, right? The first one, the 3-2, is Marcus's equation. The equation that I asked point blank to Marcus in July of 1996, where did he get this equation? He says he got it from the data after finding that that was the best equation. So that's conceptual. The other equation that Marcus was famous for inventing was this equation 3-6. I asked him, actually I take that back, I didn't ask him, because by that time I had already realized that this was just a mapping equation. And the numbers 1010 were Marcus's. If Professor Ponce wanted to develop something different, I could have put in there 900 or in 5 or whatever number I put in there. I could put crazy numbers out there and it would be my equation. The difference is that this equation is the better one, because for the Kerr number equal 1, okay, no, for the Kerr number equal 100, the S is 0, and that's what he wanted to do. So 100 in the denominator, 1,000 over 100 is 10, minus 10 is 0. That's why he did it. That's why he did it that way, okay? Therefore, the Kerr number 0 doesn't exist. But the Kerr number 1 is 990, and that's what he also wanted to do. Kerr number 1 is unheard of in floods, because there would be no flood. It would be 990 inches of abstraction. And 990 inches of abstraction is a huge amount, right? So this is the Runoff curve number method. And then we have to do the dimensionless precipitation. Like you can have a precipitation like this, or like other. You can have one that starts high, then it gets low, then high. There's all kinds of variability in the distribution of precipitation. I'm not going to get in there. Input, and we'll get to the input later on. Output description, there, that's the output. And notice in here that the hydrograph is going up, and it reaches a good number, 43,200, which is a number that relates to the data. You remember as 43,200, I believe, square feet per mile, something like that. So then the hydrograph can be, well, we calculate this, and then if you want to plot it, as Rosa did, you just run a spreadsheet to plot it. You can cut and paste that data into the spreadsheet. We have so far not been able, or have not been, it's not been able, we have really not had the wherewithal to do a calculator on PHP. It can be done. It's just that difficult. I have to hire somebody that could do this. I mean, I don't think we engineers, civil engineers, can get that deep into the programming. Yeah, online development. I was at a time at a place, and I gave a talk on the online calculators, and one of the professors told me, Professor Ponce, we're really surprised that you, being a civil engineer, are doing these calculations. We're leaving that to the computer engineers to do. I said, no, this one is half civil and half computer. So either of the two professions could do it, but it's safer that the civil does it because he knows the mechanics. The other guy just knows techniques. The other, I mean the computer guy, okay? Or the computer gentleman or lady. Okay, language, we talk about the script, the grid independence, we already explicitly talk about many times. And this is the proof of the pie right there. There are 3 hydrographs there. Delta T 15 minutes, delta T 7.5 minutes, and delta T 3.75 minutes. The 3 hydrographs. No other method can do this. Absolutely. And this came out of the program that Rosa had built. Okay. The next figure shows 3 outflow hydrographs generated by the kinematic wave model that uses backward in space, backward in time. This is the Lee model. But the Lee model that had been doctored to set the Courant number equal 1. So then there's a mistake in there, but small mistake. And if in the Lee model, you don't set the Courant number equal 1, you let it do whatever it has to do, then it comes out like this, a little uglier, because we already know the answer, okay? So we, of course, are not contention, by we state that the Lee model should not be used, and it's not used. I happen to know Lee personally. We were roommates or classmates, I should say office mates is a word. And he did this, he had to do it at the time he did it, but it was not the thing to do. But to his defense, at the time we did this, or at the time we were involved in this, it was in the early 1970s, and we just didn't know. We were all getting PhDs, and when you try to get a PhD, you got to get a PhD. The faster, the better, so that you can go out there and work. And that's what Lumir Lee was doing, as well as myself. Okay, so lack of grid independence. So we're talking here, you can see in there lack of grid independence of the Lee model. 2 Lee model, effective grid resolution. Diffusion wave model, effective grid resolution. They're all the same. I mean, to the point where it is almost so close that People may say, hey, did you do this? I mean, how did you do this? Right? Then we test other things. Rainfall intensity, it is responsive. It has to be, because the peak is IA, intensity times area. Then if the rainfall for the same area, if the rainfall intensity is 2 centimeters per hour, it has to double. Actually, yeah, 4 centimeters per hour, it doubled, as you can see. We needed to test the behavior of the method, the mechanical behavior of the method, and we did that. Rainfall duration 6 hours and 12 hours, it worked. Diffusion wave model, it worked also in here. Then changing the areas, it worked. Everything worked. Everything worked beautifully. Okay? So we had this hundreds of times. And by the way, when I did my my model, 1986, I did not do all this test. I figured I had an inkling that it was going to work because you have a gut feeling that it was going to work, but we didn't test all the cases that Rosa did. So we used her chance, or the chance that she was doing this, to test everything and confirm ourselves or convince ourselves that it was correct. Okay, so that's another example in here, effect of the rating exponent. Now, you guys know that the rating exponent could be turbulent, 1.5, or laminar, 3. And in the middle, the 225 is mixed laminar turbulent, the kind of situation that Horton found himself in the mid-30s when he was doing routing. He was doing watershed routing, but he was doing it with the conceptual models, which we already covered too. Remember, we talked about that already. Because at the time, you could only do the conceptual models. The conceptual models were theoretical, and they could be done analytically. So you could integrate, you spend a couple of days integrating an equation, no big deal. But we weren't going to do it numerically because that's not going to be a couple of days. And in fact, nobody should attempt to do a numerical calculation by hand because there's thousands, millions. How are you going to do that? Impossible, right? So if you have an error in a numerical model, you cannot say, oh, well, you know what, I'm going to do it by hand. You can't do that. It cannot be done by hand. You have to, the way to do it is that you already have an example that has a solution, which you can trust. And then you have the model, at whatever cost, find that solution. That's the only way to do it. And if it has errors, well, it has errors, you got to look at the errors in the code, etc. And these opportunities for errors are infinite. So you really need to have a clear mind to do this kind of work in order to get it done. As to the issue of whether people are actually doing models or not, I'm not going to answer that question. All I'm saying is that people are extensively using Excel, and they're extensively using HEC-RAS and HMS. In the middle, there's a sort of vacuum. The stuff that we do in the visual lab, develop new models and stuff, it's rare, but it is there. It is there. And I'm only judging here in the United States. I can't judge the entire world. I can't judge China, Japan, and other countries that may be doing something different. And I'm not aware of. Okay, so the bottom slope, it works beautifully. The bottom slope diffuses. You can see in here, the blue is diffusing already. It's diffusing already. As a matter of fact, we have a paper that we never published, which exactly talks about this subject. And that paper we never published because, interestingly enough, and I'm going to share with you something today, that it was turned down because the reviewers didn't think it was too great, but they were wrong because that does this calculation, which had not been done before. So I was thinking the other day that what I should do if I ever get into a situation where I don't have anything to do, that pick up the paper, rehash it, redo it, and republish it. But I ran out of will to do that. It's there, it's published, it's on my site, and that's it. But this kind of problem is the one that is showing in that paper. That with a slope of 0.0001, you're going to have an extension of the time of concentration. Because time of concentration is going to come over here like this, in this double, triple. So what is time of concentration? Is it the formula by Kirpich or the other formulas? And the answer is, if it's kinematic, yes, but not as if it's diffusive. So if you have a very mild slope, the formulas for time of concentration would not work. because I'm not considering the diffusion. So you need to set up a whole new way of doing it. And that work, by the way, has largely not been done. You know, there's 4 formulas to calculate time of concentration, but the only one that really is supposed to work is the last one, the kinematic time of concentration. But it's still kinematic, not diffusive. So we're talking here diffusion time of concentration. Okay, so we're done in here. This is different points, so different calculations show that in fact that's like a curve that goes like this, and so on and so forth. I'm going to finish here. I already spent too much time on this. But let me just say, this is a very nicely done piece of work, by the way, in colors and everything. We have to understand that if we do this kind of work, we got to design color in space. Space is not too difficult, but color is difficult. Engineers don't know anything about color, but you have to learn red, green, and blue and stuff like that. I learned this 20 years ago, and I have anecdotes to tell you, but I'm not going to do it. It's another opportunity, but we know the colors. As a matter of fact, Professor Ponce has a color palette because we were not happy with the www color palette. There was another gentleman from Pakistani origin who had another color palette which was very good, but we were unhappy, so we designed our own color palette in the year 2005, which is on the web, by the way. I believe it's called color.sgsu.edu. Effect of bottom slope. There it is. Effect of bottom slope. There it is. Look at this. Yeah, look at the bottom slope. How is extending the diffusion. Okay, so that's it. That's basically effect of Manning's end. The Manning's end is an effect. Effect of overlap flow area and channel length. Effect of rainfall intensity. It's all congruent with everything we have said. And here, effect of rating exponent, right? And so on and so forth. That's it. Conclusion, analysis, time of concentration, summary, etc. Okay, so I'm going to stop there. I'm going to stop there, and I'm going to move on to the next subject, properly dynamic waves. Okay, what is the first one? The first one is called, let me just go. The first one's called A Pathology of Computational Hydraulics. A Pathology of Computational Hydraulics. What is pathology? Pathology is when the study of what went wrong. You have doctors, medical doctors that are pathologists. They are look at the study of illnesses, diseases, right? Everybody knows that. But a pathology of computational hydraulics, what does that mean? It's unusual to be self-critical openly. It happens, but it is unusual. And this gentleman was self-critical. He was saying, we worked on computational hydraulics and we're going to look at its pathology now. Who is this guy? This guy is Michael Abbott. Michael Abbott is a British gentleman, but he, as I understand it, I don't know his life completely, but I understand that he worked a lot in Europe, not just Britain. And he was at one time the head of Danish Hydraulics Institute. DHI, Danish Hydraulics Institute, right. As a matter of fact, I believe that he was instrumental in leading the Danish Hydraulics Institute. He was British, but he was leading out the Danish out there. He must have been in partnership with some Danish people, whatever. The Danish Hydraulics Institute is now, I'm talking here 50 years later, leading the world in international consulting in our field, in computational hydraulics. They have a bunch of models. They have the SHE model. They have the SHE model stands for Système Hydrologique Européen, meaning French, SHE. Okay, from in English it would be European Hydrologic System. And that's a very well-known model around the world because the Europeans pushed that model. I mean, that's their model. They don't use a HMS. They don't use HMS. They got their own model. They got the SHE model, right? Likewise with the other models. So that's Mike Abbott. I had the good fortune to visit with Mike Abbott when he was a young man, 1975, They had a conference over at Colorado State, and they invited the big guys, and Michael Abbott was there. Conch was there, and other people. Yes, correct. Conch and many other people, Woolheiser. They were all big guys. I was a little guy at the time, but I was listening what they were saying. Okay, so this is Michael Abbott. That's 1976. That's a year after we met personally in Fort Collins, Colorado. Since these papers take about a year to publish, it must have been already in the oven. They were already cooking this paper by the time, or he was already, by the time he got to meet with us in, I believe, in July of 1975. So this is an interesting paper. I have not scanned the whole paper because there's only one part that is really interesting. Although if you guys are interested, go back to the journal, find it, and read it. I mean, the only thing that could happen to you is that you would learn, because this guy was at the top of his field, although he was not free from mistakes. As a matter of fact, he made a mistake in this presentation. There's only one paper. How can I say he made a mistake? Because I know the stuff. I've been at it many, many times. Okay, I said Kant made some mistakes. Okay, so pathology of computational hydraulics. So let's read what he says, because it's important. It's Abbott, none other than Michael Abbott. Nearly horizontal flows constitute the most numerous class of models currently used in practice. Now, nearly horizontal flows are the regular flows. Nearly horizontal, small slope, carrying flows in systems of channels, rivers, estuaries, coastal regions, and even lakes. The simplest of these appear to be the one-dimensional models, so-called because they can be described using only one space coordinate. That's correct. The most general one-dimensional models are the dynamic models, the Fred models, the Danny Fred models, in which two dependent variables are defined, u and depth, velocity and depth, upon the two independent variables of distance and time, and two first-order partial differential equations are then used to describe the relation between them. That means the equations that I presented to you today in Rosa's thesis. In such models, information travels both upstream and downstream. Aha! What's this? Information travels both upstream and downstream. They are dynamic models, and dynamic models have two solutions. So they got to have one wave going upstream and one wave going downstream. That is under subcritical conditions, because under supercritical conditions, it turns out that both waves travel downstream. One first, the fast wave, and then the slow wave. That's under supercritical conditions. Okay, so they must be provided with values of both dependent variables as initial conditions, and either one dependent variable or one relation between dependent variables that is consistent with the two directions. He's got an entangle in there. It's two directions, dynamic period. The second order equation has two directions. These dynamic models can be degenerated. Look at the word he's using. I don't like that. I told you I wasn't going to like this. These dynamic models can degenerate. Degenerate is a bad word, right? Degenerate. I think I would have put it simplified in there, not degenerate. Degenerate into pure kinematic models that use a relation between the dependent variables to reduce the two first order to one. So you got to, with one order first order equation is only one direction of propagation. So he's correct. I agree with the statement. It's correct, but the word of the use of the word degeneration is too strong in here and not justified. Okay, it kind of puts down all of us that have worked on kinematic waves, let alone Woolheiser. Poor Woolheiser, I hope he had not read this statement. Woolheiser is the kinematic king, so to speak, okay? A common source of error, and here is where we're going to focus in here. And by the way, I am not sure at this point, I think this is where I read it for the first time, by the way. So he educates us. A common source of error is the use of a boundary condition in a dynamic model that is really only proper to a pure kinematic model. So he laid the ground in there. He said the kinematic model is simplistic, the dynamic model is the real one with the two directions of propagation. Now we're going to solve the problem. We have a boundary condition in the dynamic model. We don't have a boundary condition for the dynamic model. So therefore, we kind of place in there the kinematic boundary condition. For example, the unique discharge state relation can be used as a unique upstream boundary in a kinematic model. But in a dynamic model, the solution itself generates different discharge state relations according to the variabilities of the flows, so that a unique relation at the boundary, at the downstream boundary, he should put in here downstream boundary, contradicts the solution within the boundary. A finely balanced model will usually go as unstable in this situation, but models with heavy numerical damping may survive, only to give erroneous results. What's this heavy numerical damping? Can you add damping into the model? I mean, it's not damping, not dumping. Damping with an A. Heavy numerical damping may survive. What is this? Well, in the dynamic wave models, there is a weighting factor which is called the theta weighting factor. And you as a user can control its magnitude. And if its magnitude is 0.5, there's no artificial or numerical damping, no filtering of the noise. But if you add it, if you increase it to 0.6, then you'll get some damping. 0.55 is the recommended value. The lowest recommended value is 0.55. But you go to 0.6 is a little better, a little better. You can go to 0.8, a little better from the damping standpoint. It resolves all the noise, but it does so at the cost of shaving up the peak. So there's a cost to be paid here. If you use 0.55, it may be weakly stable but accurate. If you use 0.95, it would be strongly stable but inaccurate. That is where we stand in here, and I will have a chance in the next 4 weeks to repeat extensively these concepts which I just thrown in here for you. Okay, so there's the issue of the weighting factor. So the weighting factor could be explicit and implicit, by the way. And what he's talking about here is explicit. But there's weighting factors that are implicit that if you don't know what you're doing, you have a weighting factor in there and you don't really know you got it. Okay? It is a good practice to build models on conservation laws, such as those of mass, momentum, and energy. Well, what he's saying in here is that the deterministic models are better than the conceptual models. And I'm not sure of that. Because then, if that would be the case, then Marcus's work for 40 years would not be worth a darn. And the fact of the matter is Marcus's work is very useful. Everybody uses it around the world. They revere Marcus for having invented that concept, which is not physical at all. Kind of physical, but it's not physical. It does not follow mass, momentum, and energy. So again, Abbott here is too strong on the defense of deterministic models, physically based deterministic models. There's 4 types of models. Deterministic, with physical equations, mass, momentum, and energy. Stochastic, which don't use anything of that. They go on the laws of probability. Conceptual, which is the kind that Marcus was doing. And then finally, empirical. In the empirical model, like the water quality models, you throw in a number in there and run with it. And we have done it in the other class, not this class. In environmental hydrology, we did it repeatedly, okay? Because there's nothing else. Okay, but models with heavy numerical damping may survive, only to give erroneous results. He quotes Verwey in there, and I believe at one time I saw that paper. Verwey is a professor of hydraulics over at one of the universities in the Netherlands. Okay. Now, it is a good practice to build models on conservation laws. 2 laws provide a solution to the problems, and there is a choice of which 2 laws are actually chosen. Okay? In the continuous case, the solutions are independent of the choice, but in the discrete difference case will be, in the discrete difference scheme case, there will, I don't understand this English here, depending upon the choice of laws. Okay, thus schemes that conserve mass and momentum will usually falsify the energy, and this falsification will generally worsen the more abrupt and rough the changes are from one point to the next. This is interesting because he's coming up with a concept that says that you have mass, momentum, and energy, and if you conserve mass and momentum, which is what you want to do, you falsify the energy. Now, I don't know exactly, because I haven't done this, it's not in my experience, why would you use all three? You only need two. You have two variables, you need two equations. And in unsteady flow, we use mass and momentum. And in steady flow, we use energy. That's in my book. So I'm not exactly sure where he's coming from here. Energy may be produced in large quantities, but for better or worse, this does not produce in the physical world. Similarly, a model built in mass and energy will usually falsify the momentum. That's not in my experience because I have not done that. I think I'm going to venture to say that he is not on very firm ground when he is saying this. But that's because only because my experience does not back him up. Okay? Now, falsification of mass also occurs in dynamic models. And Abbott is described as one model of an irrigation system that lost 50% of its water numerically. Yes, falsification of mass is not common, but it can happen if you're not careful with the formulation of the model. And remember, we did the Muskingum conch and we had it done nonlinear, and it falsified mass very little. It was 1% in 500 miles, but it did falsify mass, and we were able to prove that in fact that is the case. We wrote 2 papers on that. Poorly posed boundary conditions can especially influence mass loss, and the author recalls one such case where a stratified fuel model lost 46% of the water in its lower layer in a 20-hour simulation. I remember very clearly that in 1975, when we were talking, we meaning the group of people were talking to Abbott, we were young people and he was older, and he was talking about the falsification of mass, and he says, yeah, this is something we had to contend with. Be careful when you do your models, because if it's not right, they could falsify. So the best thing to do is, if you're developing a model, you have to check mass conservation. And we have shown that in our hydrologic models, the mass conservation is perfect. Every time you write a hydrograph with, like with Muskingum conch linear, it's perfect. The conservation is perfect because it's hydrologic. When it comes to hydraulics, then it's a little more difficult, and therefore you can have problems with the lack of mass conservation. That happens because the more calculations you do, the less accurate the model. Write that down. Professor Ponce said that. How could that happen? The more calculations I do, the less accurate? Yes. And I'm going to leave that to explain to you later, not now, but just take it from me. So if you do 100,000 calculations, nothing happened. But if you do 10 million, you have a problem. You see? How to solve the problem. That's interesting. I'm going to talk about it extensively later on. But the way to solve the problem is to put in there the filters, the controllers of the extra energy that is smaller than the grid size and so forth, and obliterate the model, or force the model to behave. That I call the aspirin, because it behaves like an aspirin. If you have a headache, I mean, you can suffer the headache, but you can also have an aspirin. And the aspirin will obliterate the headache, but it will be at a cost, some cost. We don't know exactly what it is, but there is a cost. Obviously, if you have a big headache and you take 100 aspirins, you die the next day of excess aspirin, right? Something like that. I'm not putting a number in there, but that's the way it happens. So these models can die or become inaccurate due to the fact that we have abused this issue that we have, this tool that we have, to obliterate the results just so that they can run. So we don't want to do that. We certainly don't want to do that. We are serious in this situation. We were looking for an answer that makes sense to us, makes sense to everybody, and it is reasonably accurate. If the model is not accurate, then you might as well throw it away and start all over again with something else. And that's why we talk about the grid independence of the Muskingum conch. I'm sold totally on it, because the opportunity for it to go wrong are myriad, and it doesn't go wrong. I already shown that to you, okay? So in here, these falsifications of reality may proceed quite slowly. In no, there's a mistake in here, spelling. He's got mistakes. In multiple connected system, not multiply, circulations may build up due to rounding errors in a poorly designed elimination algorithm, but they will not break through the main solution for some prototype days. At the end of this class, unfortunately, we're going to spend a lecture on two-dimensional models. It will not do justice, but we have no choice. We have other subjects to cover. This is just a show, actually, a show, just to show you that stuff is in there. If you want to do it, you could concentrate on studying. As a matter of fact, Rosa supposed to practice in the two-dimensional modeling field. She runs the two-dimensional models. And she actually, when she was with me, she never ran a two-dimensional model. But she trained to do that, and she does it very well. That's the way. You can never know everything at any one time. You keep learning. Professor Ponce is 40, almost 50 years in this business. If we could call it a business, I keep learning. Okay? So very slow developing errors can often be studied by running down to a steady state condition by setting at a fixed difference in level between the two ends of a uniform channel while maintaining constant resistance. It can then happen that the solution is indeed seen to settle down into a steady state. But then it very slowly starts a numerical itching, or psyching, not itching, psyching, which builds up ultimately to destroy the computation. So he's really talking about the pathology of our field, computational hydraulics. It could very well be hidden and eventually destroy you. When Richardson in 1908 developed the Richardson Scheme, one of the first schemes ever produced in the world, 1908. Forget about masking, I'm conscious, that stuff was later. He ran his model for a while because he had no choice, okay, because he wasn't using a computer. And it was stable and very cool. So he published his model, Richardson. It's a very common name, and I can't tell you, I don't have a quick reference right now, but I know the story. So he published the model, and he was applauded by everybody. And then when people started using the computation, particularly when we had computers or calculators, mechanical calculators and so forth, we proved that the method was unstable. My recollection is that it was violently unstable. So if you got to the 30th or 40th step, it will blow up immediately. Like boom, like this, without really telling you that it was going to blow up. And that was the famous Richardson scheme. It lacked diffusion. It lacked a small amount of diffusion to avoid, it didn't have the aspirin to avoid the big headache that it was going to cause later on. So that's history, okay? Now, the above difficulties are typical for dynamic models. Yes, yes. These guys, I mean, the Danish hydraulics at the time were pushing the dynamic wave model because the Conch method had not come up yet of age, right? So they were pushing dynamic models. So that's why he's saying in here, the above difficulties are for typical dynamic models that they're dealing with. There were the Sogrea models, the Scheme models, and European models. European models. Were they American models in there? And the answer is no. There were some professors out there, I don't remember the names right now. 2 or 3 professors, Professor Chang from San Diego State was doing his dynamic model. Not at 1976, but later I think we did it, built a dynamic model from scratch. Like Danny Fred's, following the work of Danny Fred. He did it in 73. I did it, I believe, in 78. Built a dynamic model. But these dynamic models were very well known in Europe since 61, since Preissmann. Preissmann had developed the first dynamic wave model in Europe in 1961. So he's saying he's defending the dynamic wave models, but then he says, but even the simpler kinematic models give problems. Oh, now he's going to talk about something that he doesn't know, because this guy hasn't worked with kinematic models. He worked with dynamic models. But then he does a good job in referring to somebody that knew, right? He says, for example, the simplest kinematic flood routing schemes use a unique states relation. So the differential equation should provide pure transport or translation without attenuation. You guys now see what's coming. However, it is observed that in practical calculations using these methods, an attenuation is in fact observed or obtained. Conch traced this attenuation to a numerical dispersion. Here he made a mistake. He made a mistake. He's allowed to make a mistake because it's at the forefront. It's a numerical diffusion from the corresponding transport difference scheme. Because if he puts dispersion in there, that statement is wrong. Because Conch was not dealing with dispersion. Conch was dealing with diffusion. And there's a difference between them, as pointed out by Ferrick in the year 1984. So we can't blame Abbott for being inaccurate in the year 75, 76. You can't blame him. He didn't know. That's what I told you. He's got a bunch of errors in this paper. So that the real wedge of prism storage of McCarthy is the guy that invented the wedge of prism storage. McCarthy said, there's wedge or prism storage, and I'm going to explain the attenuation in terms of wedge and prism storage. It was being modeled simply by the error. In other words, he's basically saying McCarthy didn't know what he was doing. He didn't mention names. He was saying Conch knows what he's doing. He is modeling the error, and that's the way it's going to be. Of course, the numerical damping could be compensated in the routing scheme. That's exactly what we do. Okay, but the real wedge or prism storage effects would necessitate that the state-discharge relation could no longer be unique. That is true, though. That is true. If you introduce some diffusion, well, the diffusion produced by the method is trying to emulate it gives you diffusion, but you're supposed to use it with a steady state rating. So it's not giving you diffusion, but yet it is giving you diffusion. So he's correct in here. They necessitated the state relation could no longer be unique. The paper that we're going to read on Wednesday, it's going to dwell on this subject a little more. The thesis by Lugo, 1997. Okay, so I'm done with this paper, and I purposely spent quite a bit of time on it because I think it's Abbott, and he was at one time considered the developer of computational hydraulics. He has a book, at least a book, if not two books. I don't know. I know he has a book, The Method of Characteristics, 1965. But since nobody uses the method of characteristics anymore, has been relegated to oblivion, basically. It's like Professor Ponce's Fortran book has been relegated to oblivion because nobody uses Fortran anymore. Although every once in a while, I do get people out of the blues coming out and asking or thanking me for having a Fortran book out there online that they can consult if they ever wanted to get into Fortran. Who is getting into Fortran these days? Well, that is a very interesting question. If PHP were fast, I wouldn't touch Fortran with a 10-foot pole. But the fact of the matter is that PHP is not fast. Therefore, some people have to relegate, if they have a lot of intensive computation, like I told you, Fortran is 10 to 100 times faster than PHP. How is it possible that Fortran, dating back to 1955, is the fastest algorithm? 55. He's 65 years old and is still the fastest algorithm. Does it mean that all the other algorithms and computer programs that were developed are not as good? The answer is yes. In terms of floating point arithmetic, none of them match Fortran. However, Fortran doesn't do anything else. While all these methodologies that have come up do everything. If they want them to dance, they'll dance. Okay? I'm just joking, but that's a fact. Fortran doesn't do anything other than floating point calculation. So if your problem is floating point calculation and you're concerned about time, then use Fortran. Otherwise, use everything else. We use PHP. Let me give you an example. In the thesis that was produced by Jana, the solution to the surface water, or rather the groundwater, was running in a couple, 3 seconds. A couple of 3, 4 seconds. Very intense computation. Double space, meaning two-dimensional. And the solution with a similar comparable PHP program was running 5 minutes. So there's not even 1 to 100. It's more than 100. How is it that that program could be so fast and the other one could be so slow? I cannot tell you that. I am not a computer builder, a computer, a program, but that is a fact. Because the only thing we could do is to test the models, like it's called a benchmark. You test this, it runs in 5 seconds. You test that one, it ran in 100 seconds. So the ratio is 1 to 20. That's all the practical conclusion that we can come up with. Okay, so that's basically it. That's Abbott. So now I'm going to introduce the subject because this is a very complex subject and I'm not going to have a chance to talk about it in the 7 minutes. Okay, but no, what I'm going to do is this. I'm going to show the video because the video is repetition. It's kind of repetition and the video is a little lighter and the video is 6 minutes anyway. I should say that 4 of you guys are doing HEC-RAS, and none of you chose the topic this topic that is talking about it in this paper. There were like 8 HEC-RAS topics, and none of them you chose. Since I told you that you can choose, I wasn't going to force the issue. But this subject in here is very important in practice. What you're going to hear, what we're going to say right now. HEC-RAS model can do 5 types of calculations. Oh, I don't like this stuff. The fact that it pops up. Okay. 1, 2-dimensional model, 1998. 2, 1-dimensional unsteady flow, 2003. 3, 2-dimensional unsteady flow, 2008, I believe. In mobile wave hydraulics, 2013, and this one, water quality, I don't recall the exact date, but it looks to me like, based on the record, that every 5 years the Army Corps puts another component into their model, and I'm not sure whether this may be the last one. I don't think so. Number 6 is going to be the 3D, and some people in Europe are already calculating 3D on a routine practice. I don't have any experience with that, so I'm not going to talk too much about it. So here we compare the 1-dimensional steady and unsteady. The logo of the Army Corps of Engineers. There's a bug in there. Can you believe that? Misspelling. I'll have to fix that. We spend our lives looking at bugs or trying to find bugs. Should you use steady or unsteady flow? Before you answer that question, you have to know your hydraulics. That's why you're here. Because if you don't know your hydraulics, you could say, well, take your pick. I will do whichever. And that's not correct. That is not the correct approach. The unsteady flow requires a lot more data. It is less robust. It could blow up on you, while the steady flow hardly ever blows up. Because of what Abbott was saying, you got a lot of computations, all kinds of things could go wrong, right? The answer is not straightforward. The unsteady flow is 10 times more expensive. In other words, if you charge $5,000 to do a steady flow, that's already too much. Then depends on the project. Some projects are justified in charging, but the other one would have to be 4, 5, 10 times more. Many years ago, I asked one of the people at West. She was teaching out here, and I said, "I want to ask you a question. How much do you charge for running a RAS? That's right, a RAS program?" And she said, "We'll start at 20,000. We'll start at 20,000, meaning no project can be less than 20,000 to run a RAS program." So that's money making. The RAS is money making for everybody, for West as well as for his employees. If it were not for RAS and HMS, those people wouldn't have anything to do. Fortunately, we tapped on the guys that really know their stuff because they do it in and out every day. Okay? And you will. If you get involved in this, and after a couple months of dealing with HEC-RAS, you'll be the expert. This is when we used to do lining of the channels in the 50s and 60s. Los Angeles, Escondido, San Diego wasn't done like that. It is, but to an extent. We don't do that anymore. Nobody in the right mind is doing this anymore. In the US, it's being done around the world. Oh, yeah. They still channelize the rivers. This is a river. The Santa Ana River is completely, totally channelized. It looks nice in Child's book, but there's a lot of people that don't like it. The ecologists don't like it. They say you kill all the life in there and whatever. There's all kinds of ifs and buts, and there's views on opposing views on the subject of whether we should channelize outright all the rivers or not. My opinion, of course, is that no, we shouldn't. As a matter of fact, we shouldn't channelize any river. But then, of course, there are prices to pay for that. So under steady flow, the flow is constant. It's one Q. Q upstream, Q in the middle, Q downstream. For unsteady flow, you're going to calculate the Q's and the Y's, and you're giving a Q versus time in the upstream. That's the inflow of the hydrograph. And downstream, you're given a rating, the rating. But as Abbott said in his paper, remember, Abbott said in his paper, under unsteady flow, the model calculates dynamic loop discharge ratings according to the variability of the flow. Therefore, if you downstream specify steady, unique value, it's wrong. But then the question is, but I don't know the answer. How could I specify a non-unique rating when that's precisely what I'm calculating? That would be like chicken and egg. I can't get the chicken before I go to the egg, whatever. Okay, and that makes a lot of sense. And when I talked about this with Woolheiser at one time, Dave Woolheiser, a good friend of mine, and he argued, and well, you know, he argued that the system was not really well built because you had to know the answer before you actually calculated it. And that's exactly what he's talking about here. I need to do the loop rating downstream before I actually can get the loop rating. So that was for many years considered to be a drawback. Okay, so then I talked about this with none other than Danny Fred back in the late 70s and early 80s. I said, Danny, you know this problem, right? He says, yeah, right. Danny had a lot of experience. And I said, how do you solve it? And I had an inkling that it could be solved. And he says, well, Ponce, you know we do this. And he explained to me what he did, which is exactly what we're talking about here. What you do is you artificially extend the channel and let the model generate its own state unique rating downstream. And then the model, if it's a good model, and all models are supposed to be good, then it has to start progressing upstream and generate the loop rating at the point of interest. That's exactly what happened, and it works. So it's tricky. Contradicts the solution at the boundary. That's what the word that Abbott used, right? Remember, contradicts the solution at the boundary in that famous pathology paper. Because that's the way it should look. This is a loop rating we had calculated to put in our book. The steady is single, up and down across one path, and then the unsteady is like this. This happens to be very unsteady. I had a program that could do this. So we calculated, because typically the width of the loop is not that wide. This is an extreme. This would be like a full dynamic equation that will attenuate maybe 70% within one period of propagation. That would show that kind of stuff. Loop rating produced under unsteady flow. And here we come up with a solution. Okay, so I'm going to tell you, well, I already passed my time. Maybe I should just wrap it up in here and I'll finish up when I come back. I think it's better. Okay, so I'm going to stop in here and we will continue when I come back this Wednesday.